This is a technical demo describing how to test the G.8275.1 Telecom profile. Most of the steps that will be described apply for regular PTP testing as well. IxNetwork implements both grandmaster and slave capabilities, and as such can be used to test master, boundary, transparent, and slave clocks alike. In this example scenario, we will be testing a switch, which will be acting as a telecom boundary clock, also known as a TBC. We will be looking at BMCA testing, timestamp quality testing, sync quality testing, and some important rate parameters. To configure a new G.8275.1 test, simply connect to the chassis which you have connected to the device under test, select the ports which are connected to the device, and simply add the G.8275.1 profile from the timing and synchronization category under the next gen protocols. I have done this for the first port, which will be acting as a master, and also doing this now for the second port, which will be acting as a slave. I will proceed to configure the first clock as master and rename the device group accordingly, and the second port as slave. One important note to make, because the device we're actually doing the demo on is not an actual telecom boundary clock, some adjustments will need to be undertaken. First of all is the destination multicast address, which will have to be set to forwardable as in classical 1588, and because the current DUT does not support the rates required by G.8275.1, I will also uncheck the drop malformed option. So the first thing we want to test is the best master clock algorithm, and to do this I simply start the PTP master device, and I immediately see it going to grandmaster state, and after that I start the slave device, and I see it going from listening to uncalibrated and then to slave, and it's now showing me its master clock ID, which is the master clock ID I have configured on the boundary clock. We can also see some interesting statistics, and we can see on the per PTP per port statistics view counters for each message type, and we see that we're receiving announced messages on the slave device, and that we're sending on the master port, and that indeed the DUT sees our emulated device as the grandmaster clock and has thus stopped transmitting announced messages on that port. Another important statistic on this page is the rate statistic, which shows an instantaneous message rate for each of the message type, and we can see on the slave device that right now we're receiving 1 message per second. Now, if you further want to validate the best master clock algorithm, we can go to the PTP drill down view, refresh the statistics, and on the slave tab we can check the port identity, the master port identity, and the grandmaster port identity. And indeed we can see that the grandmaster port identity is equal to the port identity that we have configured on our grandmaster emulation. Another interesting thing that we can test regarding this is in the simulate tab. We can simulate instead of a PTP grandmaster, we can simulate a boundary port that has a grandmaster connected behind it. So we'll be having a grandmaster with the clock ID of 1, and let's also modify the steps remove value. So starting the grandmaster again, starting the slave, and after the slave has synchronized, we can see the port identity, the master port identity remaining that of the boundary clock, and the grandmaster identity is the grandmaster identity of the port that we're simulating. Another important BMCA test is to verify that the bridge correctly propagates grandmaster values on the fly. So for this we'll be adding a few more statistics to this view from the stats selector button, and I'm simply going to go ahead and add all the statistics available for PTP to this view. The view automatically gets refreshed, and we want to look out for the clock class. So right now we have configured a clock class of 6 on the grandmaster device, and we want to check that if this is modified, for example, to 140, this change will automatically get propagated to the slave device. And indeed we do see at the slave device the clock class immediately being propagated to it. Going now to testing actual timestamp quality. One of the most frequent problems with devices is that they do actually not include their internal phi delays when transmitting the timestamps, and this can very easily be seen in the path delay. The path delay is the actual delay between the device we're emulating and the device under test, and considering that it's supposed to be around 4 or 5 nanoseconds for each meter of cable, right now we're seeing a pretty big value. For 1 gigabit and above, IxNetwork automatically adjusts for its internal delays, but for auto-negotiate and lower speeds, this is not the case. So for testing the timestamping quality, in this case, I'm going to force the port in 1 gig mode, and I'm simply going to start the configuration again. What we're able to see now is a path delay that's much more close to the values of the actual cable length that we have now in the setup. And we can see a path delay here of a few nanoseconds. Now for testing proper path delays on auto-negotiate or lower speeds, there are two configuration options called the TEX and RX calibration factors. Please consult the documentation for more details. Now, probably the most important thing you want to test when you're testing PTP is the actual synchronization quality, and this is reflected in IxNetwork in the offset statistics on the PTP drill down tab. The offset is the time difference in nanoseconds between the slave and its master each time a new sync message is received. A very low and stable offset means a properly synchronized clock. And because we're right now emulating both the master and the slave, and they both run on a backplane sharing the same frequency, it means that for the end node, the slave, to have a proper synchronization, that the boundary clocking between must properly synchronize frequency lock to its grandmaster. And we can see doing this quite nicely at this point. So we have maximum offset of 13 and a minimum offset of -15. Now the G.8275.1 standard specifies that when a boundary clock loses connection with its grandmaster, it must try to enter holdover state and maintain the timing characteristics that it had at the previous connected grandmaster. And to do this, and to try to test to see what happens when the connection to the grandmaster is lost, we simply go to the negative testing tab and set the sync drop rate to 100%. At this point, no sync messages are being sent from the master device to the DUT, and we can see a steady increase in the offset field. And going now to the final statistics that are very interesting for protocol testing are the inter-arrival statistics. These mean the time in nanoseconds between two subsequent messages of the same type. And this is important because this 1588 specifies that 90% of the messages have to be in between plus minus 40% of the agreed signaling interval. And you can see the current value, the max value, and the minimum value. Now, for proper testing, this must be run against an entire message population, and we do have a test composer script that has been developed with input from Iometrics that does the complete check as it's being done in the certification tests. Another very important thing to test if you have a multi-port PTP capable device is scaling. And to do this, you simply need to add more slave ports connected to the device under test. To do this, you simply select the ports in the slave device group, select the ports that are connected to the DUT on the respective card or chassis, add them to the slave device group, let the ports come up, and once this happens, we can start the whole scenario again and try to measure the same properties and parameters that we did when using a single slave port on using multiple slave ports. And you can check all of the statistics as we did before, including the path delays and the offsets in this new multi-port topology. Also worth testing is the impact traffic has on synchronization quality. And because in this scenario we are having a boundary clock in between, synchronization quality should stay the same. So to test this, we just go to the traffic tab, add a traffic item, select as source the master port, as destination the slave ports, monitor the flows by the destination MAC, set a frame size of desired length, and put this as, let's say, 90 megabits per second. Track the flows by destination MAC, and we're at this point good to go. Now we simply start the traffic, we can see the statistics for the flows here. And we can immediately see that some frames are being dropped or delayed, or there is loss incurring on some of the ports. What should not happen though is for traffic to affect, as I said, the synchronization quality. And we can again check this by inspecting the offset statistics in the PTP tab. Now, because the device I was testing with does not support the G.8275.1 profile, I will exercise specific profile configurations using a back-to-back setup. So, I'm going to now create a new config. connect two ports that are back to back. So adding the first port and adding the profile to it, and selecting the second port and adding the profile to it. Right now I'm going to set them both as masters just to demonstrate some BMC parameters, and on the G.8275.1 tab I'm going to let one transmit as non-forwardable and the other use the forwardable destination MAC. They should still at this point negotiate. So starting the protocols now. I immediately see one of the devices going into passive state because it's seeing that the other grandmaster emulation has a better priority than it. What I can test is that the fact that the priority 1 field, as specified in the 75.1 standard, has no influence on protocol negotiation. So if I change the priority 1 field to a lower value, this still remains in passive state. And on the other hand, if I set the clock class to a lower value on the master, you will immediately see the two reversing roles. So the first session is becoming grandmaster and the other one is becoming passive. Another interesting option to test that's specific to 75.1 is the not slave option. So I'm not going to enable it for the device that was previously negotiating as slave. What this will do, it will make the other session simply ignore announce messages, and at this point I can see that both of them are in grandmaster state. What could be tested here against the DUT is that the DUT behaves correctly when the other device has not slave enabled and is sending announce sensing messages, even though the DUT itself might have a better priority than the emulation. And last of the options, G.8275.1 has specific values for each of the field types that it accepts. And for example, clock class has a very restricted set of values that it can accept. And if, for example, if I set an invalid value for the clocks class, like for example 60, and apply the changes, I will immediately see the slave session going into announce receive timeout because it's ignoring the announce messages received from the grandmaster with an invalid clock class, and I can check in ngpf logs by enabling logs on this port exactly what's happening, and it's telling me that it's dropping the announce messages because clock class is not within the standard defined set, and you have the allowed values here. Now, this basically concludes the G.8275.1 demo. For more information, please check out the documentation or contact us. Thank you.